discovery of gluons. Essentially, we will discuss today quantum chromodynamics. The first color as a characteristic of quarks as a new quantum number. First, a little bit history. Color has been introduced and motivated by observation of certain hadrons, in particular delta plus plus, which enters dipoplet, so it belongs to tentlet of particles of SU3. It has the following quantum number. It has spin 3/2. And this is in the lowest state of quarks with total orbital number 0. So it's kind of the lowest state. This is because in the same family we have also hadrons which have the same property. So what is special about this delta plus plus? The special is that this is the system of 3 U quarks. And to have spin 3/2, all they should be polarized in the same direction. So now we have the problem with Pauli principle. Because we have now 3 fermions in completely the same state. Not only this particle, but also another particle like omega minus, remember we even discussed this, has been discovered, and this is the state with 3 d quarks polarized in the same way. And again, the same problem with Pauli principle. Solution to this problem has been proposed by Greenberg, Hahn, and Nambu. I think I should write all these names, and one should get the credit. You will work all your life, right, and do something. And even if you do something great, one thing, something great, already you will be kind of credited for this. And then next generation will come and will not even write your name. No, that's another point actually. When I started to do physics, I saw this is, enormous number of people are working, But in fact, there are some personalities, and the history of science also depends on these personalities. And not too many, actually, who contributed really substantially and made qualitatively new steps in the physics. So one is really to remember these names. So Greenberg, Hahn, and Nambu said that this problem can be resolved if we introduce another degree of freedom. Which distinguishes quarks with the same charge, with the same other quantities. And they call this color, and they introduce 3 colors, so that, for instance, in delta plus plus, we have U quark of red color, U quark of blue color, and U quark of yellow color. So now these are 3 different states, and there is no problem with Pauli principle. So there is quantum number which distinguishes these 3 different quarks. So they are not identical. They have another quantum number which is called color. So that U quark is present actually in 3 states. Then the wave function of delta can be written as a product of 3 wave functions of quarks. Let me put E, G, and K. And that should be antisymmetric. Since we have the fermions, the system should be antisymmetric, and so we add here epsilon, completely antisymmetric tensor, ijk, which antisymmetrize the situation. So it will be sum over all these, the same indices from 1 to 3, and so it will be sum of different terms. But it will be antisymmetric once we start to permute two of these quarks. Well, actually I should say that it's not only Greenberg, Hahn, and Nambu. So also Bogolyubov, Tavkhelidze, and Struminsky proposed us this solution. In Dubna, they were working in Dubna, probably Bogolyubov noticed me, and as it happens very often, so they didn't got enough credit for this. Very rare citations for their work. So what is interesting, this antisymmetric tensor is actually invariant tensor of SU3. So with this tensor, you can construct invariant combinations of SU3 group. That already gives some hint that certain symmetry is behind the production of color. Next step was again suggested by Nambu. He actually suggested that color is not only something for classification, which distinguishes these particles, but it has some dynamical meaning. So, Nambu. Like electric charge. So we use electric charge to classify particles. Charge 0, charge 1, charge 2 particles, so that you can use this to classify it. At the same time, electric charge has dynamical meaning because this is coupling constant of a given particle with photons. So charge has also meaning as a coupling constant. Nambu saw already in the early days that maybe color is also kind of charge with which some mediators of strong interactions couple. Next step has been done later, in 1971. That is construction of gauge symmetry of color. Which actually realized the idea of Nambu. So the authors were Harald Fritsch, Gelman, and Leutwiler. What they have suggested is that triplets of quarks of different colors, but the same flavor, form triplet of SU3 group. So that if you take U quark, U red, U blue, U yellow, they form or they transform under triplet representation of SU3 group. But now let me put C, color group. Don't confuse with what we have discussed before. We discussed flavor SU3, and the basis was U, D, and S quark. Now we have the quarks all the same type in a sense. It's U quark, but they have different color. Again, what is the meaning of this? The idea behind that there is probably some symmetry of strong interactions. So now we should formulate or write Lagrangian of strong interactions in terms of quarks before we discuss hadrons. Now quarks. So again, the same idea. You have Lagrangian, which is the functional of quarks of different colors, and also we can introduce d quarks of different colors and all other quarks of different colors. So red, blue, blue. So we have Lagrangian, which now has also color index. And this Lagrangian, that was idea, probably is invariant under SU3 transformations. Under transformation now in this basis. So color triplets form fundamental representation of SU3 group. By that time, actually already after Young and Mill's work in the beginning of 50s, it was known how to construct the gauge symmetric models, Lagrangians, non-abelian. So remember we have electrodynamics, which is gauge invariant. We have only one photon. So here idea is similar, that we introduce some new vector bosons which transform quarks of different colors. So for instance, we have Ui, it can be transformed into Uj color, and I will just write A and J, and so I, J are 1, 2, 3. And in analogy again with electromagnetic interaction, the idea is that there are some new carriers of interactions which were called gluons, which transform quarks of one color into another. Of course, there are also diagonal transformation when a given color is transformed in the same. So now we introduce this particle G, which carries two indices, I and J, right? Because it should transform I to J. So then you have invariance. So we can write part of Lagrangian. Again, analogy with electromagnetic interactions. And let me write Q in general, because the same should be written for D, S, B, charm, for all the quarks. So this is another space. We have space of flavor, just not to confuse. And so we have flavor, where we have all this U, D, S, charm, B, and then T, which you can. But there is a space of color, because all they are presented in three colors. Okay? So we have here SU3 color. Here actually we had SU3 when only 3 quarks were known, but with discovery of other quarks we have a general group SU6 if we include also top quark. So Lagrangian has the terms as Qj, gamma mu, Qi, and then gluonic field, and that will be I and J. And since this is vector field, we have to put the index mu plus Hermitian conjugate. Okay? So the difference from electromagnetic interactions is that in the case of electromagnetic interactions, the type of the particle doesn't change, so electron go to electron, muon go to muon, u quark go to u quark, and even color doesn't change. Here what's going on, the color changes when it emits gluons. So, and again, what I was saying, that already by that time people know how to construct so-called non-abelian gauge symmetries. In the case of QED, we have abelian symmetry. We have the group U1, which is abelian group. So there's also SU2, which is used for weak interactions. We have discussed it. Here we deal with SU3 group. Now to construct Lagrangian, which is invariant with respect to SU3 color, you need to have connection of indices. So here we have J, and this is J, here is I and I, and you need to make summation over J and I. So this combination is invariant. They have gluons, and the number of gluons, how many gluons, what do you think, should be to have this invariant combination? Who can guess? You see we have 3 quarks here, which have 3 different colors. 3 quarks here. So 3 times 3, we will have 9, right? And if you want to work with irreducible representations, then we need to have something which has representation A. So that it should be 8 gluons to construct invariant combination. And these 8 gluons are transformed under a joint representation of SU3. So this is the way how gauge symmetries are theories which obey gauge symmetries are constructed. So we have something which is a fundamental representation. This is fundamental representation. And then to have invariance, we need to do something which is actually multiplied by product of 3 times 3. Okay, so we need to have 8 gluons. Each of the gluons have double color indices in contrast to quarks. So 8 gluons, double color indices, and they are transformed under a joint representation. Of SU3 color. Okay. So the difference that now, in difference with electrodynamics, now we have these color indices. And we have 3 color indices. So that's transformation and representation 3. So what we have here, invariance or under SU3 transformation. And again, the meaning is, this is Lagrangian of strong interaction, supposed to be. That should be checked, of course. And it is invariant under SU3 transformations. Actually, we had this exercise to construct invariant combination when you have proton, neutron, and pi 0, pi plus, pi minus. So pi plus, pi minus, pi 0 are the joint representations of SU2. And invariant combination when you have doublet conjugate, and then a joint representation. The same idea to construct invariance. Next step is the following. Hadrons, which are composite systems of quarks, should be colorless. You do not observe color of proton or of neutron. So proton is not, showing up in 3 different types, right? So it has no color. So hadrons are colorless, So they are invariant under color transformations. In particular, mesons, which are composite system of quark and anti-quark. Now, with introduction of indices, we need to put here I and here I. And this combination is invariant under SU3, right? Now, baryons, protons, neutrons, etc. So, those are combinations of 3 quarks. And colorless combination is constructed when you put Qi, Qj, and Qk, and then use this completely anti-symmetric tensor, I, j, and k. This combination is also invariant under SU3 transformation, and this is colorless. So this is how mesons are constructed, and these are how baryons look like. Questions? So we introduced color. Then we decided to construct the theory in which color is dynamical variable. So it's actually Kaplan constant. And then we decided to extend it and to have a gauge invariant theory. And so again, in analogy with electrodynamics, we are forced then to introduce this Lagrangian, which is the simplest that we can construct. We cannot use SU2, because with SU2 we cannot solve the problem with this Pauli principle. We need to have SU3. So this is how one can, so to say, derive quantum chromodynamics. Okay.
One question.
Yeah.
In this 3×3 representation, we have 8 plus 1, and the 1 that's here...
We do not use this, so we are working with irreducible representations here. And gauge symmetry is constructed as, and you can check this, as when you have a fundamental conjugate, and adjoint representation. Well, saying in advance, in the case of weak interactions, we have doublets, not triplets. So the theory of weak interactions has this doublet structure, and we use SU2, actually, not SU3, actually SU2 cross U1. But the same idea of construction, we have doublets, we have a joint representation of SU2, which is triplet of gauge bosons, W plus W minus W0, and the construction is similar. Again, after work of Young and Mills, it was proven how to construct the theories which have non-abelian symmetries in the basis. So SU3 is non-abelian in contrast to electromagnetic interactions. Okay.
I have a question.
Yeah?
So that means gluons also has colors, because if we see like red go to blue, or
what should have the color?
I mean, do like gluons also have colors?
Yes. Gluons.
I mean, how do we know? Like, I mean, if then we will have like different gluons, right?
Yes. So these 8 gluons, precisely, they are different by color. They have even 2 color indices, 2 colors. So a given gluon has, let's say, red and anti-blue color. Okay? In contrast to photon, which has no electric charge. So here is what is interesting, that mediator of interactions has charge with respect to interactions. So let me...
I have a question.
Yeah?
So you mentioned that the hadrons should be colorless because they should be invariant under SU3 color transformation, right?
Yeah.
But I mean, what's the reasoning behind this requirement?
Because we do not see color of proton. There is no manifestation that proton has a color. By the way, it's very important, the statement, because that explains, and remember we had this question, then among various representation, it was representation 6. When you have the product of Q times Q, when we did classification of quarks and hadrons. So we constructed representation 3 times 3 bar or 3 times 3 times 3, right? But not this one. When you have 3 times 3, that is decomposed into 6 and 3. And remember it was questioned, why we do not see hadrons in 6-plets? We see octets, we see 10-plets, we see, but not 6-plet. And this is precisely because that combination, or that one, would have color. So the statement that hadrons should have 0 color should be invariant explains why we have no 6-plets of hadrons, mesons. So let me present some elements of QCD, because this is a very introductory and short introduction to quantum chromodynamics. So this is precisely dynamics which follow from interactions we just introduced, gluons and quarks. So in this theory, gluons, let me repeat, are gauge bosons. And they have charge, and they have double charge, with double charge. So this means that they have self-interactions, right? Photon interacts with everything which has electric charge. Once you introduce some particle with electric charge, you must introduce interaction with photon. The same is here. Once you introduce some object which has a color, it should interact also with gluons. And in particular, in the theory, there's interactions when you have 3 gluons in one point, and you can connect indices if you want, which means that that comes from invariant combination. Actually, I have described here coupling of gluons with quarks. But of course there are kinetic terms, and gauge invariance actually requires that you introduce this type of the interactions. And also there are quartic interactions. When 4 gluons are interacting in the same point. So this comes from kinetic term of the theory. This is very important difference from electrodynamics. Self-couplings of gluons. This self-coupling of gluons modifies dependence of effective couplings with momentum. So that modifies dependence of, let me write, effective, and I will explain what is this. Effective couplings on momentum. So what is this? Let's come back to electrodynamics, start with this. And we have couplings of particles, in particular quarks, with photon. So this is the coupling which appears in Lagrangian. Immediately in Lagrangian you have quark, anti-quark, and photon. These terms of interaction. So now so let me put in the following. I will write index mu when I deal with gluons. So here the coupling constant, actually here the coupling constant is electric charge of a given quark. So this is not the end of the story, because if you are in the field theory, you need in principle to compute corrections. So have you started to discuss something like this at QED course? No? Who knows what are radiative corrections? Who heard about this? So, we already discussed a little bit. Once you introduce this elementary coupling, you need actually to consider all possible processes which contain 2, 3, 4, 5 more couplings. In particular, you can write the process of the following type when the photon is also emitted in one of these legs and absorbed by another leg. You can have gamma and gamma. Now this is correction of the order of E cubed. So you have E here, and E here. So you can treat this in the following way. So you have your quark Q in initial state, which emits photon. So quark continue to move, emit another photon, and transforms it again to electron. And then this electron, after emission of this photon, absorbs the photon which is emitted from here. Okay? So you can look at this as you have. And then in time, because that more or less corresponds. You have 3 points of interaction X, Y, Z, and these are gammas. This is real gamma, or it's not, actually not necessarily, right? And you have one of gamma which is emitted and then absorbed. Not only this, you may have diagrams of the following type. Now you can build up many other things by just using some elementary vertex. You can build up this diagram. Or you can do the following. So quark can emit and absorb gamma. So you insert this kind of a loop into the leg. Okay? Do you have some feeling, right? What is this? Again, I will not elaborate. This is introduction, but I will use some features which we will discuss now. So this is what we have in electrodynamics. What is important that once you start to include corrections, and in fact you must do this, and what you see in the experiment, what you observe, is not just this vertex, but a summation of all these type of the diagrams. Right? You need to make a summation of all these things. That's what will be your physical coupling constant. Physical electric charge is not just this, because you have the same external content, right? So what you have is that you have photon, then something inside, and quarks. This is what you observe in the experiment. You observe transition of one quark to another quark and emission of photon. Now, how it will occur? What is the mechanism behind? This can be like just first order. It can be like this, and it can be like this, 2 loops, 3 loops, 5 loops, 10 loops, everything. You need to sum up. So that's what gives you the physical quantity, actually what you measure. You can make approximation. Say in the first approximation, I'm just using this. One important thing is that here the coupling constant doesn't depend on momentum. It's just some fundamental parameter. In contrast, when you compute loop diagrams, they start to depend on momentum. They start to depend on Q, say photon momentum. So now your coupling constant, effective coupling constant, is the function of Q. Technically, you will actually do these computations. You remember what we did. We already made one loop diagrams when we discussed flavor changing neutral current, and you do more integration over internal momentum. However, these particles also depend on external momentum, and this is how eventually dependence of effective coupling constant on momentum appears. This is the result of computation of these loop diagrams. Now let's go to QCD. That was quantum electrodynamics. In QCD, you have all these diagrams, but now gamma should be substituted by gluon, right? We have diagram gluon. Quark. This is G, I, J, I, J. And you also can compute effective coupling constant between quarks and gluons. That will contain the same diagrams as here, as in HEP-PP. You just substitute photon by gluon, but, and this is crucial, some new diagrams will appear which are related to self-interactions of gluons, because gluons are interacting between themselves, and in particular, you will have the process of this type. Precisely here we use 3-point coupling of gluons, where 3 gluons are coupling in the same point. It will be the diagram of the following type. Oh, this one. That will be. When we have a loop made out of gluons, but also it will be the diagram of funny form of this type, when 4 gluons are coupling in the same point. So, dependence of electromagnetic coupling constant on Q is such that alpha, which is E squared over 4 pi, effective, increases with Q. So the bigger Q, the bigger effective electromagnetic coupling constant. What these diagrams do, they change such a behavior, and in contrast to electromagnetic coupling, here these diagrams start to dominate, and they have opposite sign. With respect to diagrams which are similar to QED, and you have much more diagrams, because here gluons have 8 different states, and therefore number of diagrams, and you need to sum up over color also, much more than the diagrams in QED. And those diagrams dominate, and And what happens is the coupling constant, effective coupling constant of QCD decreases with Q. So let me write this dependence. Alpha QCD, which is, again, this is G squared, let me put it here, which is G squared QCD over 4 pi, as the function of momentum, has the following behavior. So actually when you do computations of diagrams, which I have written here, and make a summation, you make summation over the series of the diagram, you get that alpha, let me put QCD, not QCD, but C color. That alpha C is 1 over log Q squared over lambda squared color. We met already this before. Remember, you computed what is even distance, corresponding distance. So this is effective scale of QCD, around 300 MeVs. So what happens is the following. For large Q squared, it decreases like 1 over log. And you see this behavior. And it has a pole when Q becomes, I think, equal to this QCD of color. So actually this is around 200, 300 MeVs. So these are large distances interactions, right? Large distances. And these are small distances. Large Q squared, small distances. Here the coupling becomes very big. It becomes just diverges, right? So here we are losing a perturbation theory. This is non-perturbative regime. When I have written the diagrams, we have the lowest order for coupling, then one loop diagram, then you can write 2 loop, 3 loop, and this is what we call perturbation theory in electrodynamics. Now here, since the coupling becomes bigger than 1, much bigger than 1, of course you are losing perturbativity, and you need to really resummate all the diagrams. Here is perturbative regime. Questions? This type of behavior has been established by Gross, Wilczek, and Politzer. And they got Nobel Prize for this. They just computed correctly corrections to lowest order and have found that they have opposite sign to what we have in QED, and therefore you have such a behavior and not like this. in quantum electrodynamics. Actually, this increase in quantum electrodynamics also leads to infinity, but at very, very high momenta q squared. This is what is called Landau pole, and that was established already in 50s. The existence of such a pole in QED. In contrast here, we have pole at lower energies. The story is interesting that actually people struggle to write correct sign. There were some computations with wrong sign, and the story is that even the first computations by Wilczek were also not the signs we have now, so he corrected. It was one guy, again in Russia, with the name Hriplovich. I think he's still alive. He made these computations, has found this opposite sign to what we have in QED. That's it. He just made computations and put it. I think it's even published in some reprint. Don't even exactly know what it is. And didn't make any noise. What is important, he didn't make even kind of extracted physical consequences of this. This is also important. So you are in your exercise problem solution. You've got some number and don't care what is the meaning of this number. So always you need to think what you are getting, is it interesting or not, important, or to keep what is the scale. In some solutions I see that even cross-sections is an inverse energy squared units. What was important really to see, if you are a physicist, you need to see what is cross-section should be in centimeters squared, and you may kind of compare and to see what is this. And the consequences are what they got Nobel Prize for. This regime is what we call asymptotic freedom at large Q. This is coupling constant decreases, and actually they're very nice and very precise now measurements how this coupling constant, effective coupling constant changes. Very precise nowadays. I probably should have the slide like this. The coupling decreases, which means that interactions between quarks becomes weaker and weaker at large Q squared, because alpha is precisely the coupling which describes how quarks interact. So now we, for quarks, can write the following process: exchange of gluon. And it is this process which is responsible for interactions of quarks inside the nucleus. Coupling decreases and interaction decrease. And therefore at very high energies, interactions become very, very weak. And actually this is confirmed by what? By Bjorken scaling. Remember we discussed Bjorken scaling, and one of the assumptions behind explanation is that quarks or partons are free particles. So this is the explanation. Now at the fundamental level, QCD was constructed after scaling has been already observed and explained. This explains why indeed at very high energies you can consider quarks as free particles. Of course still there are some residual interactions, but they become weaker and weaker. In the first approximation you can consider them as free particles. So here we have strong interactions. Of course, it is very difficult to treat physics in this regime. But it is clear this is something which should explain confinement. The fact that we don't see free quarks and free gluons, there is some mechanism, non-perturbative here. Well, it's clear that if you have very strong coupling, very difficult to separate quarks, right? Already this you have some feeling of what's going on. And this is far beyond the scope of my course, this kind of introduction, but if someone is interested, then one can look at in more details. Actually, nowadays people also solve this explicitly in this regime using numerics, using lattice computations. And actually, Villadora was one who has written some papers on these lattice computations in QCD. So, here coupling becomes very strong. Some analogy of this behavior can be seen with just a rubber. This is bad. Okay, people are complaining usually when one uses this analogy, but still you may have some feeling. So that's kind of not out of any sense. Suppose you have two bodies which are connected by rubber. Now, if they're at small distances, rubber is not have a big tension, so they are almost like a free. Now, if you start to separate them, so this is small distances. So if you start to put them, then your rubber becomes like this. And you will feel the tension. So this is a large distance behavior. So here, if you do with these bodies but not trying to separate them strongly, they are almost like a free. Here you have big tension, so you cannot separate them. This is an analogy of what we have right here. Some rough analogy. Questions?
Is there any explanation of this reverse type besides experimental observations?
A reverse type, with respect to...
Unless the QED is decreasing.
Well, this is what I'm saying. At fundamental level, this is explained because you have some new corrections or new diagrams which have opposite sign to what we have in QED. Precisely, this is the big explanation in the field theory. In this field theory of QCD, you must compute these diagrams, and this is because of presence of self-interactions of gluons. You have some new diagrams, and there are many diagrams because you have color, and they dominate in these corrections, and that what reverses the sign and reverses the behavior. More questions?
Could you repeat why we have a pole at lambda QCD?
Well, it just, if you look at this behavior of coupling, which is actually the result of computations of the diagrams, and when lambda on Q becomes equal lambda, this is 0. More questions? Now, how we can check this, all these things? How we can prove the existence of color and eventually gluons? we see in the early days when it was introduced, people are saying, okay, we may introduce some other theory of quarks when the quarks, and actually that was also proposed. You will have integer electric charges and try to avoid this problem, or maybe some other degree of freedom, or what is this can be introduced. We need really to prove the existence of color. And the way we are doing, and the first and the very important actually proof was measurements of E plus, E minus, annihilation, into hadrons. And more precisely, measurements of total cross-section. As the function of square root of s. So we deal here with the process E plus, E minus into hadrons. And what has been done, the total cross-section. So this is very important that we are here discussing total cross-section, which means that we sum up over all possible final states. So we have collision of E plus, E minus. And production of hadrons in the final state. And if the energy is large enough, then we may have many hadrons in final state. According to our picture of strong interaction, the process proceeds in two phases. We have E plus, E minus, annihilation in quark-antiquark pair. And then this quark-antiquark pair is transformed into hadrons. So this is short distance process. And this is a long range distance. So, in the first phase, we have E plus, E minus, annihilation via photon into quark-antiquark pair. So what happens is that annihilation occurs in very small volume. So we have E plus, E minus, Q bar. And therefore we can consider quarks as the free particles. So this is why we can treat the first phase as really as production of free quarks and antiquarks. So if this region has radius which is much smaller than 1 over lambda QCD, C, short distance. At short distances, strong interactions are very weak. So we are in asymptotic freedom regime. And so we can consider the process as just annihilation of E plus, E minus into quarks. Now what happens when you produce these quarks? They start to separate from each other, right? You produce quarks, they start to separate. And once distance between quarks increases, the interactions between them become stronger and stronger. So what happens at long distance behavior is the following. You have quarks, quark, anti-quark, and they exchange by gluons, right? And when they separate more and more, these tensions become stronger and stronger. So what happens is, when tension is very strong, so which means that you have high enough energy relative motion of quark and anti-quark, this string or rubber is broken. And what's going on? You break it. However, it disintegrates into quark-anti-quark pair. You cannot have a free gluons. So what it is doing like this. So let me put anti-quark here and quark here. So if you have not enough energy of separation, then you will have here pi, for instance, and this is another pi. So eventually your system of quark and anti-quark will be just converted into 2 pi's. If you have high energy, relative energies of quark and anti-quark, then this process of breaking will continue and eventually we'll get many secondary hadrons. So this is what is called fragmentation of quarks in hadrons. So at each of these steps, eventually colorless systems are formed, right? So for instance, like here, you have quark and anti-quark, and they form pi, which is colorless. And that's what you can see at large distances. You don't see free quarks. Once you start to separate, they are fragmenting into hadrons. Maybe fragmenting is misleading a little bit, because when I'm saying fragmenting, something which is splitting, yeah. But here is what's going on. So they produce more quarks and also gluons and then form colorless system. So again, so if you continue, that also, these two start to separate, they will also produce break again, and you will have this process of disintegration. So now let's come back to a plus and minus annihilation.
Excuse me, Professor. Is this fragmentation process have been observed experimentally?
Well, we observed the plus and minus and then formation of pions or the final state. So we observe the process when you have collisions of electrons and positrons and hadrons in final state. So if you have energies not big, then you form just 2 pions. If you have higher energies, you may form more pions or kaons, or even produce baryon antibaryon, proton antiproton.
How big we are talking about? Like how many TeV?
Oh, no, for this, to produce 2 pions, you say it's enough to have, say, 300 MeVs. Just compute the mass which you need to produce. Okay? Or at TeVs, you have huge number of secondary particles. Masses of hadrons, say, strictly, even below 1 GeV, and you produce thousands at TeV scale. Okay? So now the process which we are discussing is the following. We have a plus, a minus, and then they produce 3 quarks, quark, anti-quark, at short distances. Now, when these quark, anti-quark to separate, so that's, say, the radius of this sphere is 1 over lambda PCD. Actually, you made computation what is the size of inverse of lambda PCD in the first exercise. And you can guess what should be the distance at which still you can consider quarks as a free particles. So when they go outside of this confinement region, then they have strong interactions with gluons, which eventually will lead to breaking, as I have shown previously, and eventually that forms of here a class of quarks and gluons, and you have a system of hadrons here and system of hadrons here at large distances. So what you form if you have enough energetic E plus and E minus, you form what we call jets of hadrons. Not they are distributed uniformly in final state. But because you produce quark and anti-quark, and again, just using energy momentum conservation, you need to have what? You need to have quark and anti-quark which are moving along one line. If you have, say, if you are in a center of mass system, and this is actually what happened at SLAC and some other places, you have symmetric plus and minus, and then you have quarks which are moving along one line, right? So, therefore, secondary hadrons, or hadrons from this disintegration, so they are along gain lines. So you have hadrons in the final state which are moving, essentially following initial motion of quark and anti-quark jets. Now let me compute the cross-section. So this is what we want to do, right? We want to compute cross-section. And the key point to compute cross-section, total cross-section of E plus, E minus to hadrons, it is enough to just consider this process, initial phase, and not care much about what happens later. Do you understand this or not? The point is that if you are interested in some specific mode of the decay, say with 5 pions, then you need really to follow all these things, are very complicated physics here because we have strong interactions. But if you are not interested in specific state, and you sum up over all possible states, then it's enough just to compute this cross-section. And you don't care about what happens after that. Okay? You just compute cross-section of formation of quark and anti-quark pair. So, that is equal to sum over possible modes, because even here you may have different modes. You can produce U anti-quark and U quark, D anti-quark and D quark, and you need to sum up over all this. So it's summation over all types of the quarks you can produce. Sigma E plus, E minus into quark, anti-quark. This is hadron. Questions asked, because that's important. Right? Again, if you are interested in total cross-section, it is enough to compute cross-section of production of free quark anti-quark. So we are doing these computations, normalizing everything to well-known cross-section of E plus, E minus into mu plus, mu minus. So let us consider first this. The diagram is similar. We have E plus, E minus, gamma, mu plus, mu minus. Now cross-section can be written immediately almost. When you have this gamma, then usually this produces 1 over S dependence, where S is total energy in the centrum of mass squared. So you have S in denominator. So this is, remember, this is typical dependence when you have exchange of photon. And formally it follows from propagator of photon. Photon has 0 mass. And this is why actually all these processes have this falling down dependence. Remember we discussed discoveries of resonances, and it was the background which actually decreased with Q squared. It precisely comes from this dependence of the processes which contains photons. So other factor 4 pi, then alpha square, because we have two electromagnetic vertices, each gives alpha, and so we have alpha squared, and then there is this numerical factor which is 4 pi over 3. Again, the 4 pi also one can figure out without any computations. You can write this also just using dimensional arguments, right? So if you neglect masses of electron and muon, and we are usually in the regime here where energies are quite high, so energy is in GeV range, then the only parameter of inverse of centimeter square is S. And so the only you can write is this one. So you can do this by dimensional ground. So that sigma should be 1 over S. And S is total energy in the centrum of mass. So S. Total energy. In the centrum of mass system. Total energy squared, right? Sorry, total energy squared. Square root of S. And actually this is precisely the 4 energy, this 4 vector of gamma, right? Because we have annihilation, this your system is transformed into gamma, and therefore this S is 4 vectors squared of photon. Now let's jump to the quarks using this analogy. And quarks are as free as muons in our analysis. And therefore for quark anti-quark pair annihilation, we will have sigma Qi or Qi equals, again we are writing this 4 pi alpha square 3s, and we need to add Qi squared. Of course, if quark would have the same electric charge as muon, we would have just the same cross-section. However, we have quarks with charge 2/3 or 1/3, and that is accounted by this Q. Right? So that Q for U quark is 2/3, Q for D quark is minus 1/3, etc. And now what we should do to compute this sigma total, we need to sum up over all possible quark-anti-quark pairs which can be produced, right? Over all possible quarks which can be produced. So introduce the ratio sigma total hadrons over sigma mu plus mu minus, precisely this cross section. We call this R, and this is equal just by the sum over Q squared I. this is common factor it just cancels. And now measurements of what experiment gave us. That has been done in particular slug, when you have a plus and minus division. And what has been measured, the cross section into hadrons total. So let me put this up, sorry, once introduced. As a function of square root of S. Again, we haven't discussed much masses of quarks, but U quark, D quarks, so they are quite light. So their masses, or effective masses, or if you want the masses which appear in chiral perturbation theory, is around say, 4 to 10 MeVs. The mass of strange quark is heavier. K mesons are heavier. It is around, say, from 80 to 120 MeVs. The mass of charm quark is, we discussed 1.2 GeVs. The mass of B quark is 4 point something of GeVs. So, MU say 4 MeVs, MD is 11 MeVs, MS is, so let me write 80 MeVs, M charm is 1.2 GeVs, MB is 4.2 GeVs. Well, I think that will be enough to reconstruct this dependence. So please help me how we will do this. Suppose we are at low square root of S. So what will be this ratio? What is the ratio? So you need to sum up quarks over quarks which are produced at these low energies. So let us consider the range below the masses of J psi, which is 3 GeVs. Right? So this is the mass of 3 GeVs. So tell me what I should put here, how I should compute this ratio R. So in this range, I can produce, which quarks I can produce? I can produce U quark, I can produce D quark, I will have enough energy, right? I can produce strange quark. If I have square root of S of colliding Q plus and minus, say in the range, say from 1 GeV to say 3 GeVs or 0.5 GeVs to 3 GeVs, right? In this low energy range I can produce these three types of the quarks. So then what do you expect here? Computing this sum. Tell me, what is the sum of charges squared over these particles? U quark, what is this? 2/3, right? Which means that I should put square, which is 4 over 9. D quark, 1/3 minus 1/3, which means that I need to add 1 over 9 plus S quark, also 1/3, right? Minus 1/3, and I need to add 1 over 9. And so I will get 6 over 9, right? and so I will get 2 over 3. Right? No, wrong. So, what is wrong? So,
We
should I?
have to consider,
Sorry?
then we have to consider also the string, the jump quark.
No, we are below 3 GeVs. So we have not enough energy. So J psi is the first appearance of charged quark. Even D bar mesons, they have bigger mass, so you cannot produce anything that's charged. So why it is wrong? Should I put here 2/3?
I mean, there are 3 possible color choices.
Exactly, yeah. We have forgotten that each of the quarks has its own color. So when we are writing this production of quark-antiquark pair, we need also to use this degree of freedom. And therefore we need to multiply this by 3. And therefore what we have here is 2. Right? It's 2/3 and then we will get 2. And that's what has been observed. I think this is clear proof of existence of color, right? That quarks have the color. Now, not only this, when you go further, above 3 GeVs, what you should add? Above 3 GeVs, you can produce charm. So we need to add to this sum the charm, which is 4 over 9 multiplied by 3. It will be what? 4 over 3. And therefore here we will have 3, 1 over 3. Now, above 10 GeVs, we will have production of B quark. We need to add to this sum B quarks, which is 1/3. We need to add 1/3. So it will be 3 and 2/3. And all this has been measured. Actually, here you have, if you look at the plots, there are these peaks with resonances. Here is epsilon J psi, here is epsilon resonances. And the behavior is like this, so which confirms very nicely that we deal with color. So let me start. I think I have 5 minutes with discovery of gluons. So this is color. Now, how about gluons? And I probably will discuss just one thing in this 5 minutes, and then we will consider the experiments after tomorrow. I discovered, yeah. The first indication that we need to add something apart from the quarks was integration of distributions of the quarks. Remember we discussed this nx, distribution of quarks over x. And it was dependence, something like that. So what you can compute total momentum which quarks carry in the hadrons. So what we measure actually, we test electric charge distribution in the quarks. So we are testing in this way number density of quarks which have electromagnetic interactions. You cannot test a neutral quarks. They don't exist most of the time. So then total momentum will be given by Pn. This is momentum of proton. And then we need to integrate dx multiplied by x and x. Actually, what is written here is multiplied by x. Actually, without x, it will be divergent. Okay. And we need to sum up this over all types of the quarks. Let me put here Q, and here is summation of Q. That is U quark, D quark, strange quark, everything what we need to do. Why it is so? So Pn multiplied by x gives us momentum which a given parton with a given x brings. So Pn, as we introduced it, multiplied by x, this is momentum of parton, of quark. Of quark with fraction s, x. N is number density of quarks. And then we do integration over x. So that should give us total momentum which quarks carry. And what has been found is that this is smaller than 1/2 Pn. So which means that you are doing integration, and it turns out that total momentum which quarks bring or carry is not a total momentum of proton, which means that something else exists which carry momentum. Okay? Not only this, what's interesting, even bigger part of momentum of proton is on something else, not on quarks. And that gives you an idea that we have some other constituents inside the proton, neutron, also other hadrons, which carry momentum of these particles. Another thing, so that was first indication that, quarks are not all the story. Another indication, and I don't finish my here, is violation of scaling. Again, scaling, exact scaling implies that quarks are free particles. Going to QCD, we know that still some interactions, although they are small, exist due to gluons. Couplings are small, but not zero, of quarks with gluons. And therefore, quarks are not completely free. And that changes also with Q square, because coupling constant depends on Q square. And what has been observed, actually, that the distributions over x and x do change with Q square. Because in the case of exact scaling, this form doesn't depend on energies of colliding particles. It's always the same in the case of exact scaling. It just depends on dimensionless parameter x. What has been observed, that with increase of Q square, well, let me put this, actually what people are introducing Q square, which is minus Q square, so that Q big square is positive. So what has been observed that N, number density, is not only the function of x, but also function of Q square. And this dependence is manifestation of violation of scaling. This dependence has very characteristic form, so that with increase of Q, that becomes sharper, and this becomes smaller. So to say, you have increase of small x partons density, and decrease here, so it's still like one. So if you go further, then it will be like this. So this is Q1, this is Q2, this is Q3, and Q1 square, let me put square. Q1 square is smaller than Q2 square and smaller than Q3 square. Distribution becomes sharper. Again, Q square is parameter of our microscope, as I always say, which actually look at your proton or hadron, and therefore the better resolution you have. And with increase of Q square, you have better and better resolution, right? So resolution is 1 over Q. And therefore your proton looks differently at small, at large and big Q square. Now let me finish by the following. Suppose you have bad resolution, small Q square, bad resolution, and you see quark with fraction x. Now, if you look with better resolution, you can see that actually this is not just a single quark, but it is something which also accompanied by gluons. With better resolution, you can just see it as a single object. Now, if you have x here, then emitting gluon, the quark will have smaller x, because here the gluon has also x prime prime, the sum of this gives you x. So which means that with better resolution, amount of momentum which a quark brings is smaller. It is shared with gluon, which is emitted. And therefore you will see more quarks with small q's, with small x, when you have better resolution. So it is because of emission of gluons you modify this distribution. That's how it can be understood. So actually here the process can be even more complicated. It may be like x emits gluon, absorbs gluon, then you have another gluon. With bad resolution that looks like a single quark. With high resolution you will have this picture, and your say electron scattering doesn't feel gluon, of course. So what electron scattering checks is at the quark, and therefore with high Q square, your electron would see the quark with smaller x. Questions? Clear? So next we discuss.
One question. Why we don't consider the mass of the top quark for the ratio that we draw on the graph?
Well, in principle we should, but we should go to higher and higher energies. What actually, even before this, changes this behavior is annihilation into Z0 also. So what we haven't taken into account that the scattering of a plus and minus, even before top quark, because top quark is even heavier, you may have annihilation into Z0, which then decay into other things, quark, anti-quark. Already these changes behavior, but the answer is yes, you need to take into account at very high energies also top, anti-top quark. But even before this process becomes more important. And to have clean situation, we're just using lower energies, because the Z boson has big mass, it has mass 90 GeVs. At low energies, photon gives the main contribution in this process. Okay? So tomorrow we'll meet at 11, right? So I might probably invite one or two of you just to help me with a solution on the blackboard of exercises. So, and Patricia has sent this mail saying that tomorrow will be a tutorial in particle physics. Okay? Okay, good.